Perfect, perfect. Okay. Can actually learn now. Yeah. Could you imagine trying to learn if your teacher wasn't wearing a bow tie? Like, is such a thing even possible? Like, scientists still don't know for sure. Um, but I don't want to have to imagine that because it sounds atrocious. Okay. So let's jump into our warm up. So from yesterday, this is basically like our last two problems that we did. Find the center, find the radius. So what that means is we need to take this from general form, put it into standard form. So let's first take this, move it over to the right side. And on the left side, we will group our x's together, group our y's together. From there, complete the square. So b over 2 squared, negative 12 over 2 is negative 6. Negative 6 squared is plus 36. So add 36 on both sides. 2 over 2 is 1. 1 squared is 1. So plus 1 on both sides. Now we can actually factor. This factors into x minus 6 squared. This factors into y plus 1 squared. 12 plus 36, 48. Plus 1, 49. So now that it's in standard form, we can just immediately determine the center is 6, negative 1. Radius, square root of the right side, so square root of 49 is 7. All right, so just practicing using the completing the square so that we can then factor, put it into standard form. Okay. So today we're going to go on to our next piece, which is ellipses. All right, so we talked about these conic sections, what they're called. So one type of conic section is a circle, which we already talked about. The next type that we'll talk about is an ellipse. So we take this cone and we don't cut straight across, but we go kind of at an angle in some way, whether it's like this or this angle or whatever. And we look at the cross section. So we take the cone apart and we look at the two pieces. The shape that's made is an ellipse. Right? You might be used to calling this like an oval. All right. But our official mathematical term we'll use is an ellipse. Neat stuff. Two types of ellipses that we can have. So the first up is a horizontal ellipse, right? Which means it's a little more flat horizontally. And the equation of the ellipse looks like this: x minus h squared over a squared plus y minus k squared over b squared equals 1. The important thing to note is that A is bigger than B. And that is how we know that it's a horizontal ellipse. So here's the best way I think to think about it. The larger number right? A is the larger number. And since it is below the x, then that means the x direction is larger, right? It's wider in the horizontal x direction, right? On the right side of this equation, it has to be 1. Okay, for circles, we're used to that right side using that to figure out the radius, but ellipses don't have a radius, so it's 1. So horizontal ellipse. We also then have a vertical ellipse, and that equation is almost identical. So this is almost exactly the same, except A is now underneath the y value. So if the larger number, remember, A should always be the larger denominator. So if the larger number is underneath the y variable, then that means the ellipse is going to be larger in the y direction, so more vertical, more kind of skinny, taller, elongated. And for both of these ellipses, it's still true that the center is HK, just like with the circle. The center is still HK. All right, so let's talk about some of the properties. All right, major axis. So the major axis is the longer of the axes. So let's see. Vertices are here and here, so they're the ends of the longer side. The major axis connects the two vertices. Which goes through the center. So of course, still in the center here is, HK. So the major axis, major because it goes across the longer portion. This is kind of like what we think of for diameter for circle. Right? Diameter goes across the whole circle. So an ellipse goes across the whole ellipse, but which part? Well, the longest part. Minor axis and co-vertices. So I think you probably can intuit what the minor axis is. Major axis went across the longest part of the ellipse. Minor axis will go across the shortest part. And the co-vertices are the points on either side of the minor axis. Foci. So every ellipse has what is called a focus, but it not only has one, it has two. And so the plural we change to foci, right? But it stands, a singular is focus. So the foci are these points that sit in the they sit along the major axis, so they sit along that longest part that goes across the ellipse in either direction. And so there's 2 for each one. Okay, I'm trying to pull up a picture here that we can use for a second. Are they specifically in that spot? No. So I'm going to explain how we can figure those out. Sorry, I'm just trying to pull up this picture, but it closed out on me. Okay, I don't have it. But so let's go back for a second. So for major axis, the way that we determine the distance between, the way that we know where the vertices are, but the distance between them is always A. Right, that largest number from the equation that we talked about before. Right, A represents the distance from the center to either vertex. For the minor axis, the distance between the center and the co-vertices is B. Right, that's smaller of the 2 numbers that we get from the denominators. And for the foci, the way that we determine the distance between the center and either one of the foci is we use a letter that is C. Okay, now wait a minute. There is no C in the equation for ellipses, and that's true. So we are going to have to instead find out what C is. Right? So the way that we do that is through this. I guess I shouldn't draw that. That kind of looks like an ellipse. But important note, this is not the Pythagorean theorem. All right, Pythagorean theorem is a squared plus b squared equals c squared. That is not what this is. This is it looks very similar, but not quite. It is a squared minus b squared. And so back to Caitlin's question about are they specifically in that spot or how do we know? Well, they're C. And so an interesting, probably the most applicable to us is if we have an ellipse and there's these 2 foci. One of the most common applications for us is that, well, so even though there are 2 foci, let's only think about one of the foci. And actually, let me change this point to yellow instead of pink. And let me think of some other point that's on this ellipse. Let's make it green. We'll make it a larger point. Actually, you know what? Let's not make it fully green. Let's let's throw some blue in there as well. And you know what? Actually, this focus, let's make it have some cool little lines coming off it. So what I'm trying to explain to you is that the setup of our solar system, right? The Earth's path around the sun is an ellipse. Okay, the Earth does not travel in a perfect circle around the sun. It travels in an ellipse. And the location of the sun is in one of the foci of that elliptical orbit. So it's pretty interesting. So it's very, very important for us to talk about ellipses in terms of planetary motion. All right, and a lot of astronomical motion of comets or meteors or satellites or things like that. Foci are very, very important for that. So every planet that goes around the sun travels in an ellipse. And so even though the size of each ellipse for each planet is different, the sun is always at one of the foci. All right, so that's pretty cool. I think it's pretty cool. But I'm just some guy with a bow tie on, so who knows? And we get it by doing c squared equals a squared minus b squared. Okay, so we're going to do two problems of practicing just graphing these ellipses. All right, and we're going to find all of our stuff that will, like the foci, the vertices, covertices, etc. So let's kick it off with the easy part. I have this equation. So let's first find the center. Wow, I'm so smart. 3, -1. Boom. Epic. Thank you. You know, I was expecting some pog champs or something, but epic, that works too. All right. From there, let's figure out we can go for the vertices, the covertices, whatever. But let me first determine what is a squared. So I have two options. I can either choose between 25 and 49. A squared is always the larger number, right? For when we're talking about ellipses, a squared is always the larger number. So a squared is 49. So already, since I can see that the 49 is beneath the y value, the larger value is beneath the y value, that this is going to be a vertical ellipse. It's going to be longer, kind of taller. So a is 7. So that means from the center, to get the vertices, I'm going to go up 7 and down 7. So 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. And I'll go ahead and write out what those specific points are. So that would be 3, 6, and 3, -8. Notice that from the center and the vertices, the x value all stayed the same because it's a vertical ellipse. So the vertices just go up and down. But if this were a horizontal ellipse, then I would be going left and right. So the x value would be changing. So it depends. You have to be able to make sure you're keeping track of, for vertices or covertices or for foci, which value should be staying the same. Should the x value be staying the same or should the y value be staying the same? Well, just think about, are you moving up and down or left and right? If you're moving up and down, like we just did, then x values stay the same. But if you're moving left and right, then y values stay the same. Okay? So if a squared was 49, that must mean that b squared is 25, which means that B is 5. So to find the co-vertices, I'm going to start at the center and go left 5 and right 5. So that would be -2, -1, 4. Oh, wait, oops. 7, -1. And again, notice this time I kept the y values the same because the co-vertices should move left and right from the center. So the y value stays the same. It's just the x value that I add 5 or subtract 5 from. Let's go ahead and we could kind of draw the ellipse right now, but let's go ahead and do the foci. So we need that c squared equals a squared minus b squared. So c squared equals 49 minus 25. So c squared equals 24. C equals square root of 24. If we can simplify a radical, we always want to do that. So hopefully we can recognize that square root of 24 is the same thing as square root of 4 times square root of 6. So that's 2 root 6. Oh, you can barely see that. But 2 root 6, I'll go ahead and write it over here. So again, I'm asking myself, should the foci go up and down from the center or left and right? Well, this is a vertical ellipse, so the foci should always be in line with the vertices, right, along that main axis. So in this case, the main axis goes up and down. So the foci will also move up and down from the center. So I'll keep my x value the same of 3. The center starts at -1. So the first thing I'll do is add 2 root 6. And then to get the other foci, I would subtract 2 root 6. So I can write it like this, where it's all together in one point of 3, comma, -1 plus or minus 2 root 6. And you need to write it like a complete spaz like I did too, so that it's going up in a diagonal line. That's really the key to making sure it's correct. Where'd my calculator go? Now to actually graph these points, 2 root 6, I don't particularly know what that is specifically. So I will go ahead and use my calculator here so I can get a decimal form so I can graph it. So -1 plus 2 root 6, it's about 3.9, okay? So about up here. And then -1 minus 2 root 6, -5.9. So about here. All right, so here's my foci. And the worst part about these ellipses is actually just sketching out the ellipse itself. Right? Kind of have to go a half at a time. I don't really have a great way to do it. You know, it's not amazing, but it gets the job done. So there's my sketch of the ellipse. I have the foci, I have the center. We're good to go. And again, most common application is planetary motion, right? In that all the planets orbit in an ellipse, and the sun is at one of the foci, the spots where the foci would go. So pretty neat. All right, let's graph one more. So same exact setup of let's just practice finding the center, vertices, co-vertices, and foci, and then putting it all together for a nice sketch. Starting with the center, it'd be -1, 1. Right, and we get that by seeing the +1, -1. Right, but remember each spot it changes the sign. So x +1 means we have -1 for the x spot. Y -1 means we have +1 for the y spot. So there's our center. A squared is 81 because we always choose the larger denominator to be a squared. Right? It could be down here or it could be here, but in this case, the larger one is 81. Which means that A is 9. Now remember, since the larger denominator is beneath the x, that means it's going to be, the ellipse is going to be larger in the x direction. So this is going to be a horizontal ellipse that is wider instead of like the last one we did where it was taller and skinnier. A squared is beneath the x, so it's going to be wider. And that tells me that from the center, so since A is 9, I'm going to go to the right 9 and to the left 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. There's one of the vertices. And there's my other vertices. There's my other vertex. Yep. We can actually list what those points are then. Y value from the compared to the center, the y value should stay the same since we're only moving left and right. So -9 would be -10. +9 would be 8. Co-vertices, so we need to look at b squared, right? So whatever denominator we didn't use for a squared, that's now for b squared. So b squared is 16, which means that b is 4. And so b, remember, determines for us the minor axis and the co-vertices. So instead of going left and right 4, we're going to go up, down 4. And to actually list out those points, since we're moving up and down from the center, we'll keep the x value the same. So the -1 will stay how it was, but then 1 plus 4 would be 5. 1 minus 4 will be -3. And we can see that fits perfectly with the points that we drew on there as well. And once we have these 5 points, I guess, we have kind of the basic skeleton of the ellipse. Right? You could go ahead and sketch out the ellipse now. You don't have to find the foci first. I mean, we're going to find the foci either way, but if you have these 4, you can go ahead and sketch it out. Or find the foci and then sketch it. It really doesn't matter. I'll go ahead and do the foci. So c squared equals a squared minus b squared. So 81 minus 16. Oop. Scroll back up. Okay. Wait, was it 81 and 16? No. What was our numbers? 81. Oh, it was 81, 16. I was thinking the other one. Okay, the last one was like the 49 and whatever. Okay, so minus 16 is 65, right? Yeah. 65. Take square root. 65. We cannot reduce that. I'm trying to think. It'll be 5 and 13, so no. C equals square root of 65, so our foci, the foci in this case should go left and right because this is a horizontal ellipse. So I'll keep the y value of the center the same, which the y value was just positive 1. Or no. Yes, negative 1, positive 1. I see. But moving left and right, so negative 1 plus or minus square root of 65. So this tells us now where those foci will be. So I just need to actually calculate negative 1 plus square root of 65. It's about 7.06, so just a tad above 7. About right here. And then negative 1 minus square root of 65. Negative 9.06. So about right here. So for this one, the foci are super close to the vertices, which can happen. It's okay. Sometimes the foci will be closer to the center. Sometimes the foci will be close out to the edges. It just depends on what the numbers are. And then once we have all that, we can go ahead and sketch. And again, this is the worst part. Oh, geez. Yeah. Could be worse. What's the point of the foci? Depending on what the problem is that we're talking about, the foci can tell us important information. So for example, the example that I mentioned earlier of if you have the Earth traveling around the sun, all the planets move in an elliptical orbit. And it turns out that the sun is actually in the spot of one of the foci. Can you go down to the bottom again? Yeah. The foci you don't need to sketch the ellipse. It's just good to know how to find for what we'll do later on. But yeah, for the actual sketch of the ellipse itself, we just need center, vertices, co-vertices, and you can get a pretty good sketch. Well, if you're not me, maybe you could get a good sketch. Aiden, is this what you wanted here? Yep. Okay. Cool. All right. So we'll go ahead and pause there today. Just getting the ideas down of a couple of the properties of ellipses. We'll work more on them next time. So actually, I'm not going to do a live stream tomorrow for class. I'm just going to take tomorrow to catch up on all my grading because all my classes, you guys, and then all my other classes have turned in performance tasks to me now in the past couple days. So I'm just going to take the day to grade everything and go to some meetings on Zoom and stuff that are going to be really fun. So no live stream tomorrow. I will still be checking for if you're requesting PFAs, so still do that tomorrow. I'll still periodically go through and approve them. You guys have been doing pretty good so far. Keep it up. Keep doing those. Well done. Oof. Okay. But we, as a class, will pick up again on Thursday, where we'll talk more about ellipses. It's sad stuff, I know.